So we're moving on with the chemical reaction in stoichiometry and some different features of chemical reactions that we can calculate. So we've learned about the stoichiometric coefficient, and it's important to understand, and if you think about it for like 1 second, the stoichiometric coefficients tell us the relative amounts of a compound that reacts or is produced in the chemical reaction. So in the respiration chemical reaction that we were looking at in the previous video, we saw that 6 moles of oxygen must disappear along with each mole of glucose. So this is not something that we can just choose randomly. It's fixed based on the construction of the molecule. And because of that, we can write within a chemical reaction the change of moles of one compound divided by its stoichiometric coefficient is equal to the change in the number of moles of another compound divided by its stoichiometric coefficient, and so on and so forth. This, we must note that, the stoichiometric coefficients of the reactants is negative, whereas the products are positive. So we have to keep that in mind when we try to do this calculation. So we can write, here I can represent any one of the molecules in the chemical reaction, that dNi, the change of any one of the molecules, is going to equal that molecule's stoichiometric coefficient times the change in the extent of reaction. And the extent of reaction applies for the whole chemical reaction. Okay, so for this epsilon is for every single molecule that's participating in the chemical reaction. It doesn't apply only to one of the molecules. It's the same for all of them. So we can use this then as one way to calculate how many moles show up in the product. So if we integrate this expression that we have here, we integrate from the moles that were present to start with in the chemical process, and we integrate to the moles at some finite time during the process, and we take the difference in the number of moles of that species present is going to equal the stoichiometric coefficient times the integral from t is equal to 0, or the change of process 0 to the actual value of epsilon, d epsilon. Okay, and when you integrate this, you end up with the number of moles of species I is equal to the number of moles present at the start plus nu I, the stoichiometric coefficient, times epsilon. And so now it matters how you write the chemical reaction. So you have to be consistent. Once you write the chemical reaction and you start doing these calculations, don't change it. You have to keep it the same as you move through the process. So let's look at an example calculation. Okay, so as I said, extent of reaction applies to the whole reaction, to all the species participating. So let's look at this process of sulfur dioxide plus 1/2 O2 goes to sulfur trioxide. And let's say we start with the 0.15 moles of SO2, 0.2 moles of O2, and 0.65 moles of N2. So now let's calculate this for each species. And we see initially we have 0.15 moles of SO2, and there's the stoichiometric coefficient for SO2 is 1. So we say minus 1. It's minus 1 because it's a reactant. Okay, this is a reactant. So the stoichiometric coefficient for SO2 is minus 1. For O2, it's minus 1/2. And here we see we started with 0.2 moles and we say minus 0.5 epsilon. And SO3 is simply equal to epsilon. It has a stoichiometric coefficient of 1, and there's 0 initial moles, which is often true for products. There's none in there to start with. Now N2 is an inert, so it doesn't participate in the chemical reaction at all. So the number of moles doesn't change. through the course of the reaction. It's simply constant at 0.65. So notice that this does not depend on epsilon. Okay, so you can sum all of these up. The total moles present at any time, you can sum all those up, okay? And if you were to sum all of these up, you would end up with 0.15 plus 0.2 plus 0.65 is equal to 1. The total number of moles at any time is equal to 1. Now let's sum up with the epsilons. We have minus 1, minus 0.5, plus 1, and nothing here. So we're left with minus 0.5. So the total moles at any time in the process through the course of the reaction will always equal N is equal to 1 minus 0.5 epsilon. Okay, so now we're going to call this negative 0.5 is our overall nu. Okay, that's the stoichiometric coefficient for the entire chemical reaction. So now we can, if we know the moles H and I, we can then divide it by the total moles, which we just calculated, and that gives us the mole fraction. So we can determine what the mole fraction present of each of our species at any time, how it depends on the progression of the reaction of epsilon. Okay, so now we're going to learn more about it next semester, but by thermodynamics, we can determine the value of epsilon at equilibrium. And that's how we're going to be able to determine the composition at equilibrium if we know the equilibrium constant. Okay, so take note that the total number of moles at any time is the sum of the individual moles. The total number of moles to start with is the sum of all the individual moles we had to start with. And the overall stoichiometric coefficient is simply the sum of the individual stoichiometric coefficients. Okay, so we're going to spend very little time in this course learning about the chemical reaction equilibrium. I believe you probably learned this in your chemistry class. This is the equilibrium constant, and you set it equal here to the individual mole fractions raised to their stoichiometric coefficients. So then we go backwards and find out how does yi is a function of epsilon, and then we can determine we can either determine the mole fractions at equilibrium or we can determine the epsilon depending on what information you're looking for. And for multi-reaction stoichiometry, each chemical reaction is going to have an epsilon. So we have to put a separate identifier here. So we can go through this, but for glucose, okay, glucose participates in both of these. So in the first chemical reaction, the stoichiometric coefficient is -1. In the second reaction, the stoichiometric coefficient is -2. You can do this for each of these, and you can get now the mole fraction of each species is going to equal the initial moles present in the process plus this individual sum of nu I epsilon I, one for each of the chemical reactions present. When we have multiple reactions, we may be interested to know what is the selectivity, which is the moles of desired product formed divided by the moles of undesired product formed. And simply calculate that. Another important parameter is the yield. The moles of desired product formed divided by the moles of desired product that could be formed. So that would assume that you have, okay, this assumes you have 100% conversion of the reaction that produces the product of interest. Okay, so there's no side reactions, and you have 100% conversion of the chemical reaction of interest. So here's an example calculation. If we feed 2 moles of ethylene and 2 moles of water, here's our chemical reaction. Okay, what is the maximum moles of desired product ethanol? Okay, we have 2 of each of these, and the maximum possible that we could get would be 2. Okay, 2 of these and 2 of these would go to 2 of those. Okay, so the maximum moles of desired product formed would be 2. All right, let's say we get only 1.5 moles of desired product. Then the yield would be 1.5 divided by 2 is 0.75. So that's pretty straightforward. Okay, so this is the video quiz. I'm giving you first one chemical reaction, and I'm telling you 50 kilograms of ammonia is fed to the batch reactor with 100 kilograms of oxygen. What is the percent excess of the excess reactant? And what is the extent of reaction? And now I'm telling you there's a second chemical reaction present for parts 3 through 5. Okay, so if 80% of ammonia fed is converted, and you have 3 mole% of the NO that is produced converted in this unwanted side reaction, then now determine the extent of reaction and extent of reaction 1 and the extent of reaction 2, the yield of the desired product, and the selectivity of the desired product.